Good morning everyone, and welcome to today's worked exam answer video. Today I'm taking a look at two follow-on multiple choice questions that are talking about the nucleophilic substitution mechanism, which is met in year 12 in the halogenoalkanes topic. And I imagine lots of you in year 12 are either coming on to this or have already had a look at this in recent weeks. So in these multiple choice questions, question 6 is thinking about the mechanism itself, and then question 7 is thinking about the name of the organic product which is being made in that reaction. So these are both AQA multiple choice questions which could appear on either an AS paper or on the A-level paper 3 paper. So as I've said before with multiple choice questions, I'm sure, if you are able to answer the question without looking at the options and then compare your answer to the options, I think that is by far and away the best approach, because you are less likely to be swayed by the options, and if you are confident in your answer and it appears in the list, then you are perhaps more likely to go with that and have the courage of your conviction. Whereas if you look at the options, you might end up being torn between one or two possibilities. And in these two organic questions, we can do exactly that. So I don't need to look at these as options for this first multiple choice question. What I need to do is just have a look at what reaction we are dealing with. So it says the question below refers to the reaction of 1-bromopropane with a solution of potassium cyanide in aqueous ethanol, and it says which is the correct mechanism for the reaction. Now, because you're not going to read the question and immediately kind of cover it up, you might have already seen in the first part of this video that all the mechanisms are essentially, well, they're not essentially the same, they are trying to show the same mechanism with a few fundamental issues in 3 of the 4 of them. So it's not a case of it's asking you, is it nucleophilic substitution? They're all trying to show nucleophilic substitution, at which point, if you know that they're all based on nucleophilic substitution, then you can go about drawing for yourself the nucleophilic substitution mechanism. Now, obviously, you don't have to do it this way, but if you can draw this accurately and with precision, it's then just a case of matching your answer to the multiple choice options. Now, had they have presented 4 different types of mechanism, you would need to know that when we start with a halogenoalkane, which is what 1-bromopropane is, we're using potassium cyanide, which is going to give us the cyanide nucleophile, that we would be getting nucleophilic substitution. It would be expected of you to know that. So in terms of what I'm going to draw, 1-bromopropane. Don't need to worry about the first CH3 and CH2, but I'm going to draw out the last carbon and its bonds in full. So then the potassium cyanide would be KCN, and we know that potassium as an ion is K+, and that means it's going to be Cn-. Now when we write the Cn- nucleophile, the minus needs to be on the carbon, and it is the carbon that has the lone pair. So that is one of the things that they will have done wrong in these options. They will have potentially put the lone pair on the nitrogen, or they may have put the negative charge on the nitrogen. And again, it's important, as I've said again many times with mechanisms, that we are precise, and that's the level of precision that they're looking for there. A negative charge at the end, not accepted. Lone pair on the wrong atom, definitely not accepted. Okay, and then what would I be doing with my curly arrows here? I would have 1 from the lone pair on the carbon in the cyanide nucleophile, and that would be attacking this carbon here. And why would it be attacking that carbon there? Because we have a polar bond between the carbon and the bromine, and bromine is more electronegative than carbon, so bromine would get the partially negative charge and carbon would have the partially positive charge. And then once we have got that first arrow showing the nucleophile attacking the delta positive carbon, we would need to have the bond between the carbon and the bromine breaking and those electrons leaving with the bromine atom, which would then become a bromide ion. And that would be my nucleophilic substitution mechanism for this example. So comparing that to the options that we've been given. In A, we've got a lone pair. We've got a curly arrow from the lone pair to the correct carbon. We've got an arrow from the bond to the bromine. So the curly arrows in that one are correct. So I've got my little green pen, my little red pen, so that we can find the correct parts and the incorrect parts. So that curly arrow there is good. That curly arrow there is good. What's missing is the charge. So there's no negative on my carbon, so therefore it cannot be A. If we then have a look at B, B looks a lot like mine. Yes, the nucleophile's on the top. Yes, they haven't drawn out the carbon with the two H's, but we've got the charge in the right place. We've got the lone pair on the carbon. We've got the curly arrow to the carbon, and we've got the curly arrow from the bond to the bromine. That all looks good. So I'm confident that B is now my answer, because that's what I drew. I was confident in my conviction there and them to match up. And at that point, I obviously wouldn't need to go any further. In terms of me doing this for you guys now, I am going to go further with it. Again, we've got a good curly arrow in C from the bond to the bromine, but even though that curly arrow comes from a lone pair towards the C, it's coming from the wrong atom. Should not be on the nitrogen there. So that is incorrect. For the same reason, it's incorrect in D too. Even though they've then got a charge on the carbon, that arrow from the nitrogen lone pair to the carbon is wrong, because the lone pair belongs to the carbon of the cyanide nucleophile. So it might be that you are happy to not draw that out and to just look through and go, yes, A's not right because of the charge, B's got the charge, so perfect. But if you're in any doubt, then, like I say, having your own version to compare to may be helpful. Moving it then on to question 7. So we're thinking of the same reaction. So it says the question below refers to the reaction of 1-bromopropane with a solution of potassium cyanide and aqueous ethanol. What is the organic product of this reaction? Now you'll see the term organic product quite a lot in organic questions moving forwards. The other product that would be made here is a bromide ion, as the bromine atom leaves and takes both electrons from that bond, and that would then be able to bond with the potassium from the potassium cyanide that we added to get the cyanide nucleophile. So we'd also get potassium bromide as a product. That's not organic. That would be inorganic. Organic products have to have carbon in them. So it's asking us what is the carbon-based product that we would get. And again, I can cover up those options and I can draw out from my mechanism up there what my product should be. So it's going to be CH3, CH2, C, and then we've still got those two H's on there, which I'll draw out again. And then we've got the C and the N, and just so that you're aware, the C and the N are bonded by a triple covalent bond. So that is my product. Now, the CN, we call it a cyanide when it's a nucleophile, but when we have substituted it and it appears on our organic product, we then use the term nitrile for that. So if I quickly flash the options, we've got nitriles or amines. So it's not an amine. An amine would have an NH2 group on there, and that would come from ammonia as a nucleophile. So amines are formed again via nucleophilic substitution, but using a different nucleophile in the first place. So then instead of the C triple bond N, you'd have an N with two H's. So it's definitely not an amine. Now nitriles, we may be able to see, because of the carbon in the CN, we've now got 4 carbons in our longest chain. And when we make a nitrile from a halogen or alkane, we will always end up with there being 1 more carbon in the product than there was in the reactant. So the reactant was 1-bromopropane, had 3 carbons. Because there's a carbon in the nucleophile, the longest chain is now 4. And we would need to count that carbon of the nitrile in our longest chain. And just in case there is ever anything else bonded onto this chain, so let's say we had another bromine atom on the other end of the initial reactant, we would need to show the position of that extra bromine in relation to the carbon of the nitrile group. So we always count away from the carbon in the nitrile group, and that carbon 1 there is included in the name of the longest chain. So this will be option C, which is butane nitrile. So it's not an amine because we have not used ammonia as our nucleophile. And it is not propane nitrile because we have to count the carbon of the C triple bond N. Now, there's another interesting, awkward, annoying, frustrating, whatever you want to call it, thing when we're naming nitriles, is that you would perhaps normally, for other things, like alcohols, it says ethanol. It's not ethanol. We drop the E and we go with ethan, and then we put the ol on the end. Here, we haven't gone butan nitrile. You have to have the E in the names of these nitriles. So it'll always be the full alkane name, then nitrile in this instance. And every type of naming of different organic compounds has its own little quirk and rule that we need to be aware of. So perhaps making some sort of master copy of each mechanism, the conditions, with accurate curly arrows, very precise curly arrows, and then how to name the products of those reactions may be useful, because when you come to the end of the year 13 work on all the different homologous series, coming back and having a look at all of them again could be quite overwhelming. But anyway, those are my questions for today. Hopefully you found watching that useful. Any questions, as always, please let me know in the comments or drop me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys.